Okay, we're going to continue 8M3. Today we're doing lesson 8. Lesson 8, similarity. Now, everything we've talked about so far has led up to the concept of similarity, and many things, many of the objects that we've talked about are actually what they call similar objects. Now, remember, we've talked about through past lessons, we've talked about congruence. Congruence are shapes that you can do rigid transformations on. So congruent objects are the same shape and the same size. So you can rotate them. You know, you can take a piece of paper and you can rotate it, and that you still have a congruent object. You can translate it, or you can reflect it, and it's still all congruent. It's same shape, same size. What we're going to talk about today is similarity and a little bit of the definition of similarity. And that will be the same shape, but can be different sizes, right? What is another thing that we've talked about in the past where you took something that's the same shape and you stretched it to a new size and kept it at the same shape? Yeah, dilations. When we dilate, we actually create similar objects. So we're going to talk a little bit about that today. We're going to go through a little bit of the lesson that you did in class today with your teacher. And we're going to show a few of those examples, and then we're going to jump into some homework help. And the homework, they jump into some concepts that maybe not you didn't go over in class, and maybe some of the things that we're going to be talking about in some of these upcoming lessons. So this homework help may help you out. So keep an eye on that. We'll do that on, I think, the last slide. So let's cut over to today's lesson, and let's start talking about some of our concepts here. So we're going to talk about similarity, right? Similarity is the key for today. Now, the informal definition of similarity are things that are the same shape and the same or different size. Generally, when we talk about similarity, we talk about same shape, different size, but actually two objects that are the same shape and the same size are also actually similar. But let's get more specific. Remember, when we talked about objects that are the same shape and the same size, there's a special word for that, right? And that is, for those of you who remember, that is congruent. Right? Congruent. Same shape, same size, but same shape and maybe different size, that is similar objects, right? So if you can take a triangle and you can dilate it and make it twice as big, you have similar triangles. So let's cut into some of the examples. One of the ones that you saw in class today, if you went to class and you're doing Eureka Math. Okay. Now the question is let's forget about this shape for a second. And what we're going to do is we're going to try and figure out. We're going to look at these two shapes. And the question are these two shapes? Question mark. Are they similar? Are they similar? In other words, are they the same shape and maybe, different size? These are clearly different sizes, but are they the same shape? And the same shape basically means, are these angles, are all of these angles the same? Are all those angles the same? Then they would be similar. Well, another way of saying it is, can I, there's a lot of ways to find out if they're similar. So one, if you can see same shape, different size, that would be a check. But it's kind of hard to see if they're exactly that way. Are they exactly a different size? Are these exactly opposite angles? So that's one question. Another question that is an equal question, and you can answer this one, yes or no. Can you do a rigid transformation and then one or more rigid transformations, and then a dilation. That would also be, and if this is true, then I get a check mark also. I can say that they're similar, because I know that if I can dilate an object, that I maintain all of the angles. So if I can do a rigid transformation and then a dilation, it's true. Another thing I can do is I could do a dilation and then one or more rigid transformations. And if that's true, then they are similar. I can do any one of these tests. And all of these tests, while the tests are different, they all can show that two objects are similar. I can do any of these things because all of these things have the same, will maintain the angles. And if I maintain the angles in two objects with the same sizes, then I have objects that are similar. And that's by definition. But it's, same shape, same size. Okay, so what do we do? What are we doing basically here in example 1? Well, you can't do a dilation to get from here to here, at least not from the origin. So the trick that they're using here on example 1 is they are going to do one or more rigid transformations and then dilation. I'm going to cut to the chase and tell you what they're trying to show you here. And so they want to take this and take a rigid transformation, which has two congruent objects. This is a rigid transformation, right? Same size, same shape. And then they do a dilation. And let's look at that. So remember, a rigid transformation, let's remind ourselves, a rigid, why does it keep doing that? Rigid transformations, there's 3 of them. One is a translation, which is just moving, or sliding. B is a rotation, that's a twist. And then C is a reflection, which is a mirror. Right? These are our rigid transformations. And these all keep it at the same size. Right? None of these things change the size of the object, nor the angles. It keeps the same angles. So what we've done here is we're just doing a translation. We're moving it down 1 and over 10. Right? So we can see that A comes down from 4 to 3, comes down 1, and then we go over 10 from 11 to 1. And similarly for B, we go down 1 from 5 to 4 and over 10 to 13. In C, we come down 1 and over 10 from 15 to 5. So we translate, our rigid transformation is a translation of down 1 and over, maybe we just say left, down 1 and left 10. And so this object and this object are congruent. So we've done one or more rigid transformations, and now we can do a dilation. And now notice if we do a dilation from here, watch this. We do a dilation from the origin. Pretty cool. We've taken each point from the origin and we've doubled. Turns out that our dilation is our R equals 2. For those of you who don't remember how to dilate objects, That we've done that in lessons 1 through 7. We've done our dilations. So this is a factor of 2 because we've gone, up. This is 1, 3. We've taken it to 2, 6. So for those of you who recall how to do that with triangles, I'll just do it real quick. We have a triangle here, and then we have a triangle here. And this side of the triangle is 1, and this side we've doubled it to 2, and this side of the triangle is 3, and we've doubled it to 6. So indeed, we have done a 2 times dilation. And you can do a similar test with B, where you've gone 3 here, and so now you've doubled it to 6 in the X direction, and in the Y direction we've gone from 4 and we've doubled it to 8. You can show it similarly on, well, let's just do them all. So here we've gone from, C has gone, we've gone from 0 to 5 and up to 2. And on our big triangle, we've doubled that 5 to 10. And we've doubled our Y direction from 2 to 4. So this is an R of 2. Okay, so again, the summary, we did a rigid transformation and then a dilation so that this triangle is similar to the big triangle. Okay, so let's look at our next example. And so now the question again is, can we do a dilation? Okay, are these similar? The question is, are these similar? Now, let's see if what we can do. Remember, we have 3 tests. One is same shape, different size, and that's just a hard thing to show. Sometimes it's easy to show, but this test A is usually generally hard. The easier thing to do would be, can we dilate and then do a rigid transformation, or can we do a rigid transformation and then dilate? And if we could do any of these 3 tests, then we know that they are similar. So let's see what we can do. Well, let's just do a rigid transformation. Or, the other thing that we can do is we can also do a rigid transformation. We could even do a rigid transformation and then a dilation, and then we can do a rigid transformation if we have to. We can keep doing these as long as we can do one or more in any order. And I'm going to show you something where we can kind of do let's just take this guy, and we're going to kind of iterate and show that they are the same size. The same shape, just different sizes. So let's see, this is 2 here, and this is 3. So let's take this A to B thing, and let's just move it so that we have watch this. Let's just take this triangle, and let's make this side be 2, and that this side be 3, and then there's the other side. And so we've basically just rotated, we've mirrored it, and we've twisted it. But you can just kind of think of it as we just kind of picked up this triangle, we turned it over, and then we twisted it, and we came to this other triangle. Maybe that's a little hard to see. So let's do it. Let's not do it that way. Let's do it differently. Let's just take this guy and let's rotate. Whoops, sorry. We're going to take this guy and we're just going to rotate him down 90 degrees. So we're going to take this guy and we're going to rotate it 90 degrees, and we're just going to kind of drop this triangle. We're going to just pretend we had a triangle and we were on the ground here, and we were holding it upright, and we're just going to take it and we're just going to drop it down like this. And what would we get? We would get a triangle. Watch this. We just lay this one down. So this point would stay here, and we'd go here. So we've laid it down on its side, and then that top side would fall over like this. And all we've done, again, is we've taken this triangle here and we've just dropped it down. Okay? So that's the same size triangle, same shape. We have just, what have we done? We have rotated it. Okay? Now, what I can do is let's do a translation. So let's translate this guy to where you can see that we have a triangle where this is our right angle. And so if these triangles are similar, then this has got to be these things have got to line up. This B has got to map to this B prime, and this A has got to map to that A prime, and this C here has got to map to that C prime. So let's give that a go. Let's just do a, so we've rotated it. Let's write down our steps here. We've rotated it. Now we're going to do a translation to line up B and B prime. So we're going to move this guy over to the left 2 and down 5, right? So we're going to go left 2 and down 5. Okay, so that we now have this triangle going to go here. This one's going to go to the left 2 and down 5. And this one's going to go to the left 2 and down 5. Okay. 1, 2, down 5. So here we got B. So left 2 and down 5. 1, 2, 3, 4, 5. So that's now point A. Now this is going to go to the left 2 and down 5. And that's our point C. So we have now translated, right? So now we've translated our triangle, right? We've rotated it, and then we've rotated it 90 degrees. We rotated 90 degrees, and then we translated it, left 2 and down 5. And now our last thing we can do is we can do a dilation. Now, typically, we've done dilations from the origin. But watch what I can do. I can do a dilation from point B, and we're going to dilate each point from point B, and we're going to dilate it how many times? Well, let's see. This side is 1 time smaller, so we have to go 2, 3. Let's see. So this side is 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, if we dilate a point about itself, it just stays still, if you can recall that from an earlier lecture. So if everything is, how far is it from B, and we're just going to dilate 3 times. R equals 3. Okay, so if we dilate about point B, we got to go straight through point A. Three times, and B's got to go straight through point C, and we're going to go 3 times. So our new points are A prime and C prime, and B prime is right on top of itself. So what do we have? we have taken our original triangle and we've used rigid transformations and then a dilation, and we've created congruent triangles. So this is indeed, so triangle ABC is indeed similar to triangle A prime, B prime, C prime. Pretty cool. Okay, hopefully you hung with me through that explanation. We're going to do a lot more of these in the upcoming lectures, in the upcoming lessons. Okay. Now we're going to keep moving on. Hopefully this made sense to you. This is the first time. Notice this is the first time we've dilated about a point that is not the origin. So if that was a little bit confusing to you, then I apologize, but this is, I've always said that 99% of the time we dilate about the origin, but you can dilate about any point, and all dilation is blowing something up or shrinking it down. So you can see that if you can line two triangles up where one of the points is on top of another point, then you can just blow up the other two sides. Then that's the same shape. That's a triangle with the same shape, just a different size. We'll probably do more of these going forward. Okay, let's move along. So now we're going to get to some homework help. Now, there is a question on your, so let's just look at this. Now, my question for you is, are these two shapes similar? Why or why not? And so now that this is a you try. You try, pause. Pause and think, and look back at your definition. I'm gonna give you the hint here. Look back at your definition, same shape, same or different size, informal definition of similarity, and see if you can use that on this homework help. Okay, now I assume you're back and you've tried it and thought about it, and the answer is no. Of course not. These cannot be similar because they are not the same what? Shape. Right? They're not the same shape. How do we know that? It's because to be the same shape means that the angles are all congruent. Are all congruent. Well, here we have 4 angles, and here we have 3 angles. So if we have, right, 1, 2, 3, 4, and here we have 1, 2, 3. So these cannot be the same shape. They have this different number of vertices. The angles are not congruent. So no, they are not similar. Okay, now here's the second homework help. This is homework help number 2. And now this is a concept, this is a concept in the lesson where the easy answer is going to be in lesson number 9. So we don't have lesson number 9 yet. And so you're going to learn the shortcut in 9 to figure out how to know that these two triangles are similar. Now, I want you to think about it, and I want you to pause and think. Pause, think, and try. Pause, think, and try. Okay, I assume you're back, and we're going to go through the explanation. Now, remember that you can, when you're trying to figure out if two triangles are similar, you can dilate if you can dilate, then do rigid transformation, then the triangles are similar. Okay, that's kind of my hint. And watch what we do here. So what we're going to do is we're going to take our smaller triangle and we're going to do the dilation. Now, if we dilate this triangle with an R of 3, so let's take the little one and we're going to use an R of 3. And why are we using an R of 3? Because my small side is a 3 and my small side of the big one is a 9. So if these triangles are similar, the 3 has to map to that 9, right? The small side's got to be still the small side. And so if that is 3 to 9, my R is equal to 3. Okay. So if I were to dilate this small triangle, we'd make a triangle, well, it would be, you know, you'd end up with a triangle that was like this. You know, something like this. And because we're going to blow this guy up, right? So if we blow this up with an R of 3, we got to blow it up along these lines here. Right, and we're going to go 3 times along this line. And so we're going to get a point right here. We're going to get a point, you know, right here. And we're going to get a point right out here. And it's got to be, right? There's some cute, cool tricks. It's got to be parallel to this line. So let's make our triangle. Okay. And after we've made, let's make it a different color. Let's make it yellow. And I didn't do a perfect job of dilating it, but we do know, remember back, you got to remember back, right? If our R is 3 and this side here is 3, then this side here has got to be 9 because you scale. Each side is the original size times the R factor. So this side was 4, so this side has to be 12. This side has to be 9. And if this side was 5, this side is 5 times 3. And so that's 15. Okay? So we've dilated this guy 3 times bigger. And remember, the way that we knew it had to be 3 times bigger is we took our small side of 3, and then we knew it had to blow up to a size of 9. So times 3. And the neat thing is 4 times 3 gets to 12. There's our 12. And then our long side is 15, and there's our 15. It just happens to work out. And so we have 2 triangles now that are the same size. Right? So they don't look the same size because I didn't do a perfect dilation down here. This side should be a little bit out here. But if I would have used proper tools, this would have been exactly the right size, 9, 12, and 15. And that's the calculated size using an R of 3. Now, if you have a triangle that has a 9, a 12, and a 15, and another one that has a size of 9, 12, and 15, then we know they are the same size. And we know they are the same shape. So we can do a rotation on this, and then we can do a translation on this, and we know that these things indeed are the same shape and the same size. So the answer is yes. And how did we know? It's because we did a dilation and we got two triangles that are the same size. And then we know once they're the same size that we can do, our rotation, translation, and reflections to make them be sitting on top of each other. Well, the answer is yes. Now, the short answer, and I'm going to go back and I'm going to just give you a preview all the way to lesson. I'm going to give you a preview of lesson 9. Watch this. Okay, preview of lesson 9. Bonus, look, a color. I don't think I've ever used this color before. Preview of lesson number 9. And that basically says two triangles are similar if there is a number that I can multiply each side by and get the corresponding length of a side on the other triangle. Okay? And so what is that number? We've already calculated that number. So the number is R equals 3. 3 times 3 is 9. So now I have to use that times 3 number. So 5 times 3, same number, is 15. And then 4 times 3 is 12. It's the same number each time. So I know that these triangles are similar. So let's use that concept and do the last homework help problem. And the question is are these triangles similar? And yet they don't look similar, right? This one we have a right angle here, and so there's no angle that matches up to be a right angle on this one. So we know the answer is no. But let's use what we learned on the last lesson, or on the last slide. And let's say, okay, well, this side is going to map to the shortest side over here, which is 6. They're all 6. But this one is times 2 to get to 6. So the question would be, can I multiply each side by 2 to get to a corresponding side on the other side? I have to multiply 5 times 2. And do I get a matching side? And the answer is no. So these, I can't match up the sides because I would need a side that was 8, because 4 times 2 is 8, and 5 times 2 is 10. So I would need a triangle that had a 6, an 8, and a 10 to be something like this one. Well, let's just do it over here just a second. I'd have to have a triangle like this one. To be similar to that one. Because in this case, this side would be 6. This side is 8. And this side is 10. So if I had a 6, 8, 10 triangle, that would be similar, because then my R factor would be a 2 times 2. 5 times 2 is 6, or sorry, 3 times 2 is 6. 5 times 2 is 10, this long side, and 4 times 2 is 8 for this other side. Okay, so let's just load this up with a happy cat. Now, the good news here for you is that we are going to review. We're going to review this a few more times in the upcoming lessons. So this is kind of an introduction to similarity. we've had all the building blocks. We haven't used the word similar very much. Going forward, we're going to learn about some more properties of similarity. Similar triangles are hugely important and powerful out there in the real world, but also in geometry and future math that you will be doing. So we will we'll carry on the good fight. Keep learning math. That's the building blocks of so much of what we do. So much of what we do in the real world. Those of you who know math know how to control the world, manipulate the world. You're going to do fantastic in your future jobs. And by the way, the SAT is very dependent. Doing well in the SAT, very dependent on your ability to do math. So let's call that a day and let's make it a wrap.